Um, Good afternoon to everybody. My name is Fabrizio Sebastiani. I'm with the Computer Science Institute of the Italian National Council of Research. And today I'm going to talk about some joint work done with my colleagues Andrea Esuli, Alejandro Moreo, and Andrea Pedrotti. And the theme of the talk will be multilingual text classification and easy and proven solutions to carry it out that don't compromise with effectiveness. So when I speak about multilingual text classification, what I mean is carrying out text classification in a multilingual environment. So in an environment in which the documents can be written in one of several different languages. And of course, here I'm not just talking about classification by topic. This could be classification by sentiment. It could be classification by author, as in authorship analysis. So these simple, effective ways that I'm going to talk about, in talking about them, I will encounter themes and topics such as classifier ensembles, transfer learning, and word embeddings. So let me first define what I mean by multilingual text classification. So again, I mean, we are talking about a situation, a scenario in which each document is written in one or a finite set of predefined languages, M languages, and a situation in which the classification scheme, the set of classes that sometimes I call the code frame, is the same for all languages. Here, this situation is represented by several flags representing different languages: English, Italian, French, Spanish, Chinese, etc., and represented by the fact that, for each of these languages, there may be a training set and test set. So, I mean, this is a scenario which is very common in, say, multinational organizations, such as the United Nations or UNESCO, or companies. I mean, large multinational companies such as IBM or Vodafone, as long as, in multilingual countries. Okay, so I guess that there are something like 57 different countries in the world which have more than one official language. And, India, for instance, is a sterling example. I will define three variants of this multilingual text classification task. The first is the sort of a trivial variant, okay, which I will call the multiple monolingual text classification. And the idea is that multilingual classification here is solved as M different independent monolingual classification tasks. Okay, so we train on English and test on English, we train on Italian and test on Italian, independently of each other. So the second is what is sometimes called the polylingual text classification scenario. And here the idea is to try and attempt to exploit the synergies among different languages. Okay, so given that the classification scheme is the same for all languages, it's sort of intuitive to think that, say, a training example in French might be exploited, to also carry out classification in Spanish or Chinese. Okay, so in this particular scenario that I call polylingual, which is sometimes called the few shot scenario, the training examples exist for all languages in the set, okay? At least some training examples. And indeed, the very notion of few shot tends to indicate that for some languages, I mean, there might be just a few training examples so that, we are justified in looking for the synergies, from between this language and other languages. So here the idea is to perform polylingual text classification in order to improve over monolingual classifiers. Okay, so improve on the performance that we might obtain just by training on the training examples from the specific language, but by also leveraging on the examples that come from the other languages. A third scenario is called cross-lingual text classification. Sometimes it's called the zero-shot scenario. And again, there is an attempt to exploit synergies among different languages, but there is a different situation. Okay, so here we assume that training examples exist only for the source languages. Okay, so for the languages for which there are training examples, but sometimes not for some of the target languages, which is, let's say, the languages for which we are interested in testing, in classifying documents. So in this scenario here, we see that for Italian and for Spanish, we have no training examples, okay? And so in a sense, in this case, we are very justified in looking for help from English, from French training examples, from Chinese training examples, okay? So this is indeed called a zero shot because there are zero training examples for some languages. And here, the idea is not just improving on the naive version. The idea is to generate classifiers for languages for which you otherwise couldn't generate a classifier. Okay. So the setting that we will study today will be mostly polylingual. Okay, so there are indeed some training examples for each languages. And we will concentrate on polylingual multi-class classification. So the situation in which there are more than 2 classes at stake. There are a couple of variants of them, important variants, a single label polylingual classification, which basically says you need to pick exactly one class out of the n different classes available, and multi-label classification, where you can pick any number of classes for a given document out of the available n classes. Indeed, cross-lingual and polylingual classification are both instances of what we might call heterogeneous transfer learning. So we all know, I mean, what the basic idea is of transfer learning is to reuse information, to reuse knowledge, to transfer knowledge about a problem that we have from a source domain and transfer it to solving the same problem in a different target domain, which is different although related. And here, in our cases, the problem that we are going to tackle is classification. The information that we want to transfer is training examples, and the domain is a language. Okay, so this scenario is very useful to address the training data bottleneck, okay, which is especially serious for what people call the under-resourced languages. Okay, so throughout the world, I mean, there are more than 3,000 languages which are spoken on a day-to-day basis, you know, but most of the resources, okay, dictionaries, labeled data, unlabeled data, concentrate on really a handful of languages. Okay, so there are many languages that risk to be left behind, languages for which there are no resources. And here we are looking at the case in which the resources are the training data. You know, so indeed, you know, polylingual text classification represents what we might call a form of massive transfer learning. So the idea in polylingual classification is that is a metaphor of everybody helps everybody. Okay, so all of the training examples contributes or are called to contribute to the classification of all unlabeled examples, okay, irrespectively of the language of provenance. Okay. And the idea is how we can achieve that. Okay. So there are various solutions in the literature, but one direction we'll be looking at today will consist in trying to eliminate the differences between the different languages. Okay. So like in the figure on the right side, you know, it's a sort of, we'd like to start from a situation in which we have Chinese documents, Italian documents, French documents, and we put them through a funnel out of which we obtain just documents, okay? Documents that are, in a sense, in the same space, you know, irrespectively of the language of provenance. And the method we are going to look at today is a method that draws inspiration from this figure and indeed is called funneling, a method that relies on a classifier ensemble method, you know, for doing heterogeneous transfer learning. So the idea of funneling is to work with a two-level classification architecture, okay, which consists of a set of language-dependent base classifiers that are here represented by these black diamonds, you know, and the language-independent meta-classifier, which is represented by this black diamond at the bottom. So the idea here is that when we have test documents, unlabeled documents, say here, we have a bunch of unlabeled Chinese documents, which are represented by this reddish rectangle. So one of them is represented by this black band. Okay, so we have a set of vectors, represent these Chinese documents. We'll have here a classifier for, Chinese documents that will output plots. It will output for each document a set of confidence scores, a set of classification scores. One classification score for each class. Okay, and so the interesting idea here is that what happens for Chinese also happens for Italian, also happens for English. Okay, and the idea is that the size of the vector and the meaning of this vector is the same as the analogous vector for Italian. Okay, because the size of the vector is the cardinality of the set of classes. Okay, and so each dimension of this vector represents the same class. Okay, so these classifiers output homologous representations. Output representations which are, in a sense, language independent. They are language agnostic. And so they can essentially be vertically stacked. We can take all of these vectors and put them through a meta classifier, which takes as input representations of the documents, which are framed in terms of vectors of classification scores, and outputs, what a classifier is meant to return. So a vector, again, of n classification scores through which the final classification decision can be obtained. Okay, so that's all. I mean, it's a very easy method, okay, which has several advantages. Okay, first of all, as I was, it works perfectly fine for multi-label classification, for single label classification, even for ordinal classification if you want, so it's very flexible. Okay, the second advantage is that it is completely learner independent. So we can have a support vector machine. We can use support vector machines for our base classifiers, or we can use random forests, or we can use Bayes, or we even can use different learners for different languages. Support vector machines for English, random forests for Italian, Bayes for Chinese. Okay. It is also independent from representation model used in Bayes classifiers. So we might want, say, to use, let's say, bag of words for English, or character n-grams for Italian, etc. And it also, it's completely flexible in terms that there is no requirement that the training set should be either a parallel training set or a comparable training set or what. And this is represented by the fact that these different squares here, these different rectangles have different sizes. Okay, so we see that, Italian documents, Italian vectors are wider than Chinese vectors, but Chinese vectors, we have more Chinese vectors than Italian vectors. Okay, so these differences don't really matter. And a further advantage is that there is no requirement for multilingual dictionaries or for machine translation services. Okay, so what is the basic philosophy here? The basic philosophy, of course, is that this very notion of funneling, maps different non-overlapping feature spaces, into a common feature space. Okay, because here the feature spaces, we have features which are very, very much language dependent, but the features in the space that is returned, are just posterior probability. Let's say are just confidence scores, which, the features are the classes, the classes in our classification scheme. And basically the idea is that what it means is that these posterior probabilities or confidence scores that return are aligned across languages. So vectors returned are homologous, So what is the potential problem here? Okay, so different classifiers might return, vectors coming from incomparable sources, okay? Because you can't really compare, the vectors returned from a Chinese from different classifiers, basically trained on different training sets. And here the solution, of course, will be, let's make them comparable. So what we can do is to convert the individual classification scores, into what people call well-calibrated posterior probabilities. Okay, so there are many off-the-shelf, packages for doing calibration. One typical method for doing calibration is to pass the confidence scores through a sigmoid, and the calibration method, basically what it does is simply picks the optimal sigmoid for converting these scores that might range, either on specific subinterval or on the entire real, or on the entire set of real values, converting them on the 0-1 interval. So a calibration that we will perform independently for each classifier we generate. Of course, this calibration sometimes is necessary, sometimes it's just desirable. So for instance, SVMs and AdaBoost, we all know, that they don't return posterior probabilities, and instead, naive Bayes returns posterior probabilities, but they tend not to be well calibrated. Okay, so while, say, learners such as logistic regressions indeed don't need this calibration step because they are known to not only to output posterior probabilities, but also to output well calibrated posterior probabilities. So essentially, the idea of calibration is here needed in order to make the outputs of different Bayes classifiers be comparable. So how do we train a funneling system? It's very easy. We train the Bayes classifiers using the monolingual training sets, and then we use these, we basically reclassify the training examples via one of these two methods, either via the train classifiers or via a k-fold cross-validation. So once we have done this, we map the classification scores into well-calibrated posterior probabilities, via a calibration routine. And then what we do is to use the posterior probabilities of training examples for training the meta classifier. Okay. So I've actually said that there are two methods for classifying the training examples, and classifying them via trained classifiers basically is what we call the FAN-TAT method, where TAT stands for train and test, while FAN-KF-CV stands for training them via k-fold cross-validation. So to cut a long story short, the idea is that, in both these methods have sort of are slightly suboptimal, because of course, when you use FAN-TAT, the Bayes classifiers tend to generate higher quality representations for the training data than for the test data, because in a sense, we are using we are classifying the training examples via the same classifiers that have been trained via the same examples. Okay, so this is slightly strange. Okay, so using k-fold cross-validation is better, is more theoretically well-founded, but has, in a sense, the opposite problem: the fact that the Bayes classifier generates lower quality representations for the training data than for test data, because in k-fold cross-validations, the classifiers you use are trained with a smaller quantity of data than the entire training set. So the idea is that we are going to choose between the two via experimentation. So let me come through to an interesting distinction. You might have wondered, what is the distinction between funneling and a well-known method, stacking or stack generalization, as proposed by David Wolper? It's quite different, because in stacking, essentially the Bayes classifiers are just, say, different types of classifiers, say one trained via support vector machines, one trained via random forests, one trained via naive Bayes, maybe. But essentially, what they do is they return decision scores, that are meant to be juxtaposed. Okay, so the idea here in stack generalization is that the very same document should go through all of the Bayes classifiers, okay? And the decision scores that are returned should basically contribute to a common representation. Funneling is very different because each document goes through only one Bayes classifier, okay? And, in a sense, the representations which are returned are vertically stacked in a set instead that horizontally stacked. So the two systems are quite different. Okay. So you might wonder, so how well does this system work? Okay, it's very simple, but let's say, does it deliver? Okay, so we have run a number of tests on large multilingual collections. So on two large multilingual collections. One is very well known, Reuters corpus, volume 1, volume 2. It's a sort of a comparable corpus, okay, which consists of 9 languages, 73 classes, and from which we have taken 10 different samples, each consisting of 1,000 training examples and 1,000 test examples per language. Okay. The second is the well-known JRC Acquis collection, while Reuters Corpus Volume 1 was consisted of news. JRC Acquis consists of laws published by the European Parliament, okay, in several of the official languages of the European Community. Okay, so this is a parallel corpus. So indeed, one document is the translation of the other. Okay, so here we have 11 languages, 300 different classes, and again 10 samples consisting of roughly 1,000 training documents and 4,000 test documents. Our tests, we used SVMs with linear kernels for the Bayes classifiers because linear kernel is well known to work on well on text classification on vectors which are sparse. But of course, the meta classifier is not going to work on sparse vectors, but on dense vectors of posterior probabilities. Okay, so for this case, we actually chose the radial basis function kernel. Okay, we used several baselines for testing our results. One is the naive system. Okay, the naive system is the let's say simply running different monolingual classifiers. Okay, not attempting to exploit any synergies between the different languages. And 3 other important baselines from the multilingual text classification world. One is cross-lingual explicit semantic analysis, distribution correspondence indexing, and lightweight random indexing. And we used a couple of measures, evaluation measures, both F1 and K, which is sort of a proxy for balanced accuracy. And each of them is both in the micro averaged and macro averaged versions. Okay, so what can we see from the results? Okay, so here is essentially is a plot where we can see for the 5 different systems here, for the 5 different cross-lingual classification systems, we can see the percentage of improvement with respect to the naive baseline in terms of macro average F1. Okay, so what we can observe here is that first of all, the 2 funneling systems, FUN KFCV and FUN TAT, basically are the only 2 systems that never underperform, the naive baselines, which doesn't happen for lightweight random indexing. It doesn't happen for cross-lingual explicit semantic analysis. It doesn't happen for distributed correspondence indexing. So in a sense, there is more consistency, more stability. Okay. And a second thing that we might notice here is that among the two versions of our funneling system, there is one that consistently outperforms the other. And this is FunTAT, the Fun Training, Train and Test, which outperforms the funneling system based on k-fold cross-validation. And this is, of course, very good news, okay, because the system that uses k-fold cross-validation is something like k times more computationally harder to train. Okay, so the computational cost for, of course, for running k-fold cross-validation is much higher. So, I mean, these are some results, you know, in tabular form. I will not go through it, but, you know, the good news is that, you know, throughout the data sets and throughout the various measures, you know, the funneling system based on train and test tends to outperform most others. So in 6 cases out of 8, you know, this is the best system. So, I mean, I will not go through other results in detail, but I want to a bit touch base on what are the intuitions behind funneling. What does funneling learn exactly? So, something that funneling doesn't learn, okay, is to combine scores from different classifiers. This is something that stacked generalization does, okay? But here our meta classifier receives just one set of scores for each document, unlike in stacked generalization. So the rationale is different, okay? So one thing that the meta classifier learns is actually to exploit the stochastic dependencies between the classes, the correlations between the classes, for the simple fact that the meta classifier receives, you know, vectors that consist of posterior probabilities for all of the classes at the same time. Okay, so it is in a position to exploit these correlations among classes, which is, you know, the basic tenet of multi-label classification learning. Okay, so there is another factor. So the meta classifier indeed learns to classify documents in any language from training documents in any language. Okay, so instead of just focusing instead of just leveraging on the results on the training documents for a specific language, we have training documents coming from all of the languages. So if we have 10 languages, we have 10 times more training examples, okay, assuming that we have the same number of training examples for all language. Okay, so we have these two basic contributing factors. And of course, I mean, one curiosity is to ask ourselves, which of the two factors contributes most? And in order to do this, we have run experiments in which we have factored out one of these, each of these factors at the same time. So on the left, you can see here, you know, the results of funneling, train and test, because we now forget about the k-fold cross-validation variant. We here see on the right, you know, the results of the funneling system in multi-label mode and in polylingual mode, as we have seen it up to now. So this bar is slightly different. So we look at the same, but in a binary version. Okay, so we still accept contributions from all of the different languages, but we focus on one class only. So if we have 100 classes, instead of running a single, you know, funneling system for the 100 classes, we run 100 funneling systems that work for one class only. You know, so the vector of posterior probabilities which is returned consists of one entry only, one dimension only. You know, Instead, here, we do the opposite. Okay, so we stick to the multi-label version. So the base classifiers return entire vectors, of posterior probabilities for classes, but we focus on monolingual. Okay, so we just use one initial base classifiers, no ensemble learning. And instead here we have the naive baseline run in binary mode. Okay, so where does the improvement come? Essentially we see that most of the improvement, comes from moving from monolingual to polylingual. So accepting the contribution of the training examples of different languages, while an improvement of much smaller magnitude comes from moving from the binary set to the multi-label set. So the effect, the multi-class factor, so exploiting the stochastic dependencies between classes, works, but works to a smaller extent. What really works is the multi-language factor. Okay, so accepting the contributions of training examples from different languages. So this is a fun plot where we actually tried with some ablation studies to figure out which languages benefit most and which languages contribute most in the JRC-ACWIS dataset of European Union laws. And the interesting thing is that well, what might not be expected is that English, in a sense, is curiously enough, the language that benefits most from the other languages, benefit most and contributes the least. While German is the language that contributes the most and benefits the least. Where, of course, I mean, these exercises, these experiments have been run, say, by removing, let's say, comparing the naive baseline with funneling in terms of deciding how much a language benefits, and while in terms of discussing how much a language contributes, we basically run an ablation study in which we plug in or out the training examples for a certain language. More interesting is this plot, okay, in which we look at how the contribution of funneling evolves. The interesting plot is the top one here, where we basically on the x-axis we have the proportion of the training examples for the target language. Okay, so these points, these data points, okay, for when the proportion is small, basically represent situations in which we have very small quantities of target training examples, which represent the case of, say, low resource languages. And what we can see is that the relative improvement, that means the improvement we obtain by using cross-linguality via funneling with respect to just using the naive monolingual version, is sort of unsurprisingly much higher for smaller proportion of target training examples. Okay, so in a sense, I mean, when we have few training examples for the language we're interested in, the contribution of other languages tends to be high or very high, while this contribution tends to flatten out, although, I mean, remain to a significant level, when we have a sizable enough set of training examples for the target language. Okay, so is this efficient? Yes, it is efficient because, especially in the training test version, it tends to be among the several baselines we have tested, either the most efficient or one of the most efficient systems. Essentially because, I mean, there is no important computation times aside, perhaps, the time devoted to classifier calibration. So let's move a bit further. Okay, so how can we improve from this, in a sense, very simple, very naive system, you know? So one of the questions we might want to ask is, aside from the vectors of possible probabilities, can we bring to bear some additional knowledge? Well, the answer is yes, you know, as long as this additional knowledge, we can encode it into vectors which are aligned across languages. Okay, so vectors where each dimension has the same meaning across the different languages. So we have seen an example in which correlations between different classes, you know, bring benefit. Okay, in our standard funneling system, you know, this was one of the factors that brought about benefits. So the question is, can we do more? You know, indeed, I mean, there are several other types of correlations in data, you know, and correlations that we might want to exploit, that we might want to bring to bear. So one type is, say, word-class correlations, okay, how a word and a class correlate with each other, you know, and also word-word correlations, you know, as we all know them from word embeddings, okay. So, you know, the idea is we might want to exploit, you know, different views of the same document, which are the same, which are, of course, I mean, language aligned. And this is the basic idea behind what we call generalized funneling. So generalized funneling is a slightly different architecture, similar but with important differences, similar to funneling but with important differences. The idea here is that, you know, unlike the standard funneling, you know, the vectors that we input to the meta classifiers are, in a sense, multifaceted. You know, one vector comes from, let's say, the base classifier, but we have other vectors too. We have other views of the same document. So in a sense, we generalize the notion of a first-tier classifier to the notion of a view generating function. Okay, so the base classifier is just a function that generates one particular view of a given document. Where can we get other views? Okay, so in a sense, you know, we might come up with other view generating functions, you know, and the idea is that once we have these different view generating functions, we aggregate the representations generated by all of them into a single vector that, of course, has to be aligned across languages. Okay, so what we have done is we have run tests with two interesting view generating functions. Okay, and these functions are functions that return document embeddings that are aligned across languages. And let me show these two types. So one of the two view generator functions we have shown is multilingual unsupervised supervised embeddings. Okay, so the so-called muses. Okay, so this is embeddings that were proposed in this paper by Kono and colleagues, and which essentially consist in task-independent word embeddings, which are independently generated for each language, and then aligned across languages by an external process, which is essentially an adversarial process in which a generator basically tries to generate embeddings in a common space and fool a discriminator into not understanding which language the embedding comes from, you know. So these muses essentially capture word-word correlations, you know, as standard embeddings, which are quite different, of course, from the class-class correlations that we exploited in standard funneling. So muses are essentially available for many languages, for 30 languages, made available by the proposers, by the authors of this paper. So there is a second type of embeddings, a second type of a view generating function that we use here. This is word class embeddings, okay, something that we have very recently proposed ourselves. And instead of, so these are word embeddings which are task specific. Okay, so word embeddings which are specialized for solving, for classification, and specialized for solving this particular classification task. And so they are word embeddings of whose size is the cardinality of the set of classes, which are independently generated for all of the languages from the language-specific training sets that we are using also to train our base classifiers. So these embeddings capture word class correlations, unlike the word-word correlations of the muses and the class-class correlations of standard funneling. And these embeddings are also natively aligned across languages. They don't need any external process to align them because they are born aligned, essentially because all of them basically are of the size, the set of classes. So each dimension of the embedding represents the correlation of the word with a certain class. How well does this work? This is good news, again, because we actually on tests we run, we actually witness the fact that generalized funneling equipped with the muses and word class embeddings is actually the best system. It outperforms, aside from the standard, all of the standard baselines, it also outperforms the standard funneling system. In 4 cases, well, in 3 cases out of 4, while in the 4th case is not, the result is not statistically significantly different from the best one. And the 4 cases being the combinations of 2 different data sets and 2 different classification measures. So, conclusion. So, where we can go from here, So what we have seen is a very simple method for doing polylingual classification. A very simple, especially in the original funneling version, it's really a straightforward method. It's a method that can be made more complex at will by moving to generalized funneling, to adding new views, by adding new view generating functions. Okay, so where can we go from here? So it would be interesting in a sense to tackle other supervised learning tasks which are different from classification, because the funneling system is not really, there's nothing in the funneling system that says that this is for classification. So multilingual quantification could be one, where quantification is saying, estimating class prevalences, or multilingual information extraction. So other classification scenarios too could be considered, say multimodal classification, so where multimodal, I mean, instead of using different languages, we have different media, say text and images. Well, I mean, this can be done as long as the code frame is the same. So say what we are actually trying to do now is to doing a classification of products, such as product reviews or product descriptions, where we have, say, from Amazon, we have the images of a product, but also textual descriptions, the same product, and we could, one important, way forward would be tackling different code frames. Essentially here we have made the assumption that the code frame, the classification system, the classification scheme is the same throughout all languages. There might be situations where these classification schemes might be partly language dependent, partly culture dependent, as we all know. And of course, probably, the most important way forward would be to tackle not few-shot classification as we have done here, but zero-shot classification. So the true cross-lingual scenario in which we have 0 training examples for certain classes. Indeed, we are, what I haven't shown today is some results which are a bit too recent to show. We have indeed performed zero-shot classification with generalized funneling by generating a slight modification of the architecture that allows, generalized funneling to work, let's say, even in the case where we don't have the specific training examples for a certain language. I think my presentation ends here, and I thank you for your attention.